This is WLOG on the air with cs407 numerical analysis, introduction and preliminaries. As John Gerstein is fond of saying, the math has to start somewhere. So how about here? John also notes that numerical analysis is not rocket science. Well, actually it is totally rocket science. A lot of this stuff originated during the 1950s and 1960s during the space race in the Cold War. We were interested in rockets at that point in time, and rockets are still pretty cool today. My first exposure to this came during the 1970s when I started programming computers, and the 1980s when I was majoring in mathematics. At both points I was probably more interested in Rocket to Russia by the Ramones than rocket science. And since we're quoting folks, let's throw in Joey Ramone, hey ho, let's go. So the objectives for this course are to provide an overview of methods for solving scientific problems using computers. In particular, we'll be looking at engineering, science, and technology apps. That means we won't have many applications from the social sciences, accounting, information retrieval, or artificial intelligence. In other words, we're just going to be covering the sad stuff. In addition, the material is fairly introductory, so the authors won't provide an in-depth treatment of it in some cases. They do hope that students will want to engage in further study after this course, as do all professors. We're also interested in understanding the underlying processes rather than just getting the answer. Yes, your graphing calculator can get the answer for you, or software such as Mathematica or Maple can as well. But how did they program it to derive that answer? And that'll be one of the things we're interested in answering. And in the words of every advertiser, certain limitations, exclusions, and restrictions do apply. And in particular, numerical computations are almost invariably contaminated by errors, and it's important to understand the source, propagation, magnitude, and rate of growth of these errors. Fortunately, this offer is still valid in Hawaii, Alaska, and Puerto Rico, so we can continue with it. In terms of limitations, we're almost going to have some type of error in the representation of the answer due to the limitation of machine precision. Sometimes the methods themselves will have a certain amount of approximation inherent in them. So it's important to understand not only how the method works, but how they can fail. And Edgar Dijkstra, the great computer scientist, said, in the good old days, physicists repeated each other's experiments, just to be sure. Today they stick to Fortran, so they can share each other's programs, bugs included. And we'll see some of those bugs and errors. So let's start with significant digits of precision. You probably know these from your studies in primary or secondary school. You've probably also seen them come into play with physical sciences such as chemistry or physics. Significant digits are the digits beginning with the leftmost non-zero digit and ending with the rightmost correct digit, including any final zeros that are exact. So let's take a look at an example. Here we have a 2 meter by 3 meter sheet of steel that's cut into two equal triangular pieces. And you can see these in the green here. What is the measurement of each one of these triangles? Well, the short answer is we can use the Pythagorean theorem. In particular, c is equal to the square root of a squared plus b squared, which is, in this case, is equal to the square root of 2 squared plus 3 squared. 4 plus 9 is 13, so we have the square root of 13 is 3.605551275. And according to the calculator on my little Mac Mini at home, the result was 3.6051275463999. And we can verify this accuracy by squaring the number, and we get 13 on the same calculator. But a bigger question is, how seriously do we take this number? In particular, how seriously do we take 3.605551275? Seems like a great number. I would take it seriously. But any real sheet of material is not going to be exactly 2 by 3. Basically, anything you go down to HPM and buy is not going to have that exact measurement, even if they cut it really closely. So even if you have a measurement error of 1 millimeter, which is pretty small, we suddenly get a range for the hypotenuse. So that hypotenuse can now range from 3.6042 to 3.6069. What if we want the diagonal to be exactly 3.6? Well, then we can solve for 3 minus c squared plus 2 minus c squared equals 3.62, which is equal to c squared minus 5c plus 0.02 is equal to 0. And that equation is really nice because we can use our good friend the quadratic formula that we learned in high school or secondary school and basically derive c is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And if you run it through your calculator, you get 0.004. So that means we can cut off 4 millimeters from each side to get a triangle that is the size of 1.996 by 2.996 meters. We can't claim any greater accuracy for the diagonal given this range that we had before, given the potential of the 1 millimeter precision of the cut. And one of the lessons in life is that we're never 100% accurate in real life. Let's take a look at another example. Here we have a system of linear equations. If you're interested in the math or a bit rusty with your linear algebra, the authors of the text provide a complete solution on page 4 to 5. What you see here is if we solve this for 3 significant digits, we get an answer of y is equal to minus 547. If we solve for y with 4 significant digits, we get 343.9, and if we repeat for 10 significant digits, we get y is equal to 3.5629 times 10 to the second, which is about 356. And basically you get a range of answers, and depending on the number of significant digits. And one of the lessons here is that we shouldn't round off prior to calculating the results. And again on this slide you see don't round off prior to calculating the result. We have 2 pictures here, and this is figure 1.2 from the text. What we can see here is there's some degree of uncertainty in lines. Errors from measurement or round off errors. Then basically what we get is a small trapezoid for the answer instead of a sharply defined point that we would expect in pure mathematics. The right hand side of the diagram shows that the closer these lines are to being parallel, the number of possible solutions can increase, and somewhat dramatically. Anyway, loss of precision can happen in a number of ways. Measurement errors, round off errors, or subtracting nearly equal numbers in the computer due to limitations on machine precision. Now let's turn our attention to errors. We have about 3 different definitions of errors. So suppose that alpha and beta are 2 numbers, where beta is an approximation of alpha. The error of beta as an approximation of alpha is alpha minus beta. The absolute error of beta as an approximation of alpha is the absolute value of alpha minus beta. And the relative error of beta as an approximation of alpha is alpha minus beta divided by the absolute value of alpha. So the relative error is usually the most meaningful of these measurements in practicality, and alpha may in fact be the exact value or the best known value that we have. Let's take a look at an example of this. So let's let A1 be 1.333, B1 1.334, A2 0.001, and B2 0.002. We'll find the absolute and relative errors of B1 as an approximation of A1. Well, the absolute error is 1.333 minus 1.334, and that's 0.001. The relative error, we divide by the absolute value of alpha, and we get 0.00075, which is fairly small and seems like it would be a good approximation. Now, if we repeat that for A2 and B2, the absolute error, once again, is the same, 0.001, but our relative error is 1, which is pretty high. So even though they both have the same absolute error, the relative error tells the story, and we would say that B2 is not a great approximation of A2, even though A1 is a good approximation of B1. Accuracy and precision. Accurate to end decimal places means that you can trust end digits to the right of the decimal place. And accuracy to insignificant digits means that you can trust a total of n digits, both right and left of the decimal place, as being meaningful, beginning with the leftmost non-zero digit. Be careful, these are two different definitions. The second corresponds to all the digits, while the first corresponds to the digits to the right of the decimal. Let's move on and take a look at some examples. Suppose you have a tape measure that's accurate to 1 millimeter. Well, in this case, a measurement of 12.345 meters, that's a-okay because you're accurate to 1 millimeter, or 1/1000th of a meter. A measurement of 12.34567 is a bit questionable. In any case, 12.345 would give you 5 significant digits, whereas a measurement of 0.076 only has 2 significant digits. And in some cases, it's interesting to note you may think you have more accuracy. Consider 1.2 plus 3.45. Well, that's equal to 4.65, but you only have 2 significant digits of accuracy here. That's because 1.2 may be due to some rounding. Say you rounded 1.24 down to 1.2, or 1.16 up to 1.2. In general, the result is only accurate to the number of significant digits used in the calculation. There are a couple more examples of this phenomenon on page 7 of the text, and I would encourage you to look at those. So, speaking of rounding, let's look at rounding and chopping. So, there are a couple different ways to do rounding, probably even more, but let's talk about 2 of these. Round to even works in the following way. If the last digit is greater than 5, we round up. If it's less than 5, we round down. And if it's exactly 5, we round to the nearest even. Round to even is known as statistician or banker's rounding. Over a large data set, it tends to reduce the rounding error, given that an equal proportion will probably be rounded up and down. Chopping, a little less precise. It discards all the digits that follow the nth digit. And, of course, rounding tends to produce less error than chopping. If we look at the example of 0.217, rounded to even is 0.22, and if we just chop it to 2 digits, it's 0.21. Now for the main body of the material from this section. Nested multiplication, Horner's algorithm. There's a bit of a sidebar on page 8 about the history of computing pi. It's worth a read if you're interested in the history of mathematics. In general, the authors seem interested in that area, and also discuss some non-European origins of mathematics throughout the book. If you're interested in the European perspective, I really like Men of Mathematics by E.T. Bell, or Howard Eves' History of Mathematics. If you're interested in the non-European origins, see The Crest of the Peacock. It's a great read. I have a link to the Amazon page for that text in the footnotes of this slide. So let's talk about nested multiplication. Consider this polynomial, a sub 0 plus a sub 1x plus a sub 2x squared plus a sub n minus 1 x to the n minus 1 plus a sub n x to the n. To evaluate this and do it in an efficient manner in the computer, we can group in terms of nested multiplication. In particular, p of x is equal to a sub 0 plus x times a1 plus x times a2 plus all the way out to x times a sub n. On the next slide, we'll see some pseudocode for this nested multiplication. And keep in mind, a pseudocode is a compact and informal description of an algorithm that uses the conventions of programming languages, but omits the detailed syntax, so you don't focus on the syntax or the accidents, as Brooks would put it. When convenient, it can be augmented with the natural language. It helps us to organize ideas before implementing them in an algorithm. Here we see the pseudocode for the nested multiplication. We assume here that the coefficients have been stored in an array A, and you'll also note the use of the left pointing arrow. That means the value to the right is stored in that location. The pseudocode may seem a bit confusing at first, but this is the most efficient way to proceed. You'll note that there's one addition and one multiplication for each time the loop is traversed. Hence we have n multiplications and n additions, which is the minimum number possible, and it avoids all the exponentiation. This nested multiplication procedure is known as Horner's algorithm or synthetic division, and it once again, it helps us to avoid all the exponentiation. So let's take a look at an example of nested multiplication. Consider this polynomial, 5 plus 3x minus 7x squared plus 2x cubed. We can turn this into a nested multiplication, namely p of x is equal to 5 plus x times 3 plus x times minus 7 plus x times 2. Here we've avoided all the nasty exponentiation that's involved and just focused on the additions and multiplications. In addition, Horner's algorithm can be used in the deflation of a polynomial. Deflation is the process of removing a linear factor from the polynomial. If r is the root of the polynomial p of x, then x minus r is a factor of p. And the remaining roots of p of x are the n minus 1 roots of the polynomial q that we get when we factor out x minus r, of degrees 1 less than p, such that p of x is equal to x minus r times q of x plus p of r. And q of x will be a polynomial of degree n minus 1 with coefficients b sub I, as you can see in that last bullet point. Let's take a look at some of the synthetic division pseudocode. And again, the algorithm probably won't make a lot of sense to you until we see an example. The text also doesn't do a great job of explaining how this works too well. So let's work through an example to clarify things a bit. So what I'd like to do here is use Horner's algorithm to evaluate p of 3, where p is the polynomial x to the 4th minus 4x cubed plus 7x squared minus 5x minus 2. So what we do is we arrange the calculation as suggested in the book. Here I've used a table instead of a division, but it works pretty much the same way. Now we put a 0 here underneath the 1, and then we add 1 plus 0 to get 1. Now what we're going to do is we're going to take the 1 and multiply it by 3 and put it in the next place over under the minus 4. So we have minus 4 and 3 times 1. And then we add the two of them. Minus 4 plus 3 is minus 1. Now we're going to take that minus 1 and multiply by 3 and put it under the 7. That'll be minus 3, and we add 7 and minus 3 to get 4. Now we take the 4, multiply by 3, and then put that result 12 underneath the minus 5. Minus 5 plus 12 is 7. Finally, we take the 3, multiply by 7, down here, move it here, 21, and then we add minus 2 and 21, and we'll get 19. And it turns out that p of 3 is equal to 19, and we can express p as x minus 3 times the remainder, which is x cubed minus x squared plus 4x plus 7, and then add the 19 on to the end. There's another example on page 10 that's good practice if you want to work through some of these. We can also use Horner's algorithm for evaluating the derivative of a polynomial, and here's the pseudocode for that. As before, it won't mean too much to you, but let's take a look at how we can use this in an example. So let's use synthetic division to find p of 3 and p prime of 3 for the same polynomial we did p of 3 for. Well, it's also good to note there's a small typo in the book for this problem. It corresponds to example 9 on page 11. If you take a look at the example, it'll be the same as what I have listed on this slide. So finding p of 3 is pretty easy because we already did that one before and we know that it's 19. But again, you can work through this. 3 times 1 is 3, minus 4 plus 3 minus 1, minus 1 times 3 minus 3, 7 plus minus 3 is 4, 3 times 4 is 12, minus 5 plus 12 is 7, 3 times 7 is 21, plus minus 2 is 19. So that works pretty easily. Now, to find p of minus 3, we just repeat the process with the results from the previous calculation. In particular, the 1 minus 1, 4, 7 that we have in the bottom row. So 3 times 1 is 3, minus 1 plus 3 is 2, 3 times 2 is 6, 4 plus 6 is 10, 3 times 10 is 30, and 7 plus 30 is 37, so p prime of 3 is 37. So, as a result of applying Horner's algorithm in this example, we see p of 3 is 19 and p prime of 3 is 37. And this brings us to another point the authors make in this section. In scientific programming, we often get pairs of easy and hard problems. For example, in cryptography, it's pretty easy to multiply two numbers together, in particular two large primes. However, it's really difficult to factor large prime numbers or to factor any number. It takes a lot more work to do that. And for polynomials, it's easy to find the power form given the roots. Going the opposite way, that's a little bit harder. So you get these easy and hard problems. You'll also see them in boundary value problems and in finding the eigenvalues and eigenvectors of a matrix. Note that in numerical analysis, a hard problem means a high polynomial degree algorithm, but not necessarily NP complete or NP hard. Of course, we might see a few of those in our journeys as well. So to aid us on this journey, there's some mathematical software, and there's quite a few pieces that can help us. Well, procedural languages such as C, C++, and even good old Fortran are handy for solving these problems, and there's also great mathematical software out there such as MATLAB, Maple, Mathematica, and Octave. But keep in mind, in solving the computer problems, you should focus on gaining insights and better understanding of the numerical methods involved. So, in summary, in this section we focused on the following ideas: absolute versus relative errors, and definition of errors along with significant digits, nested multiplication of polynomials for efficient evaluation of them, and deflation of a polynomial using Horner's algorithm. Next time we're going to get into some Taylor series, so I would invite you to put on some relaxing James Taylor songs. You can go to Carolina in your mind, or even Mexico, which sounds so simple you just want to go. Trust me, you'll probably want to be anywhere but here.